We tend to think of artificial intelligence as um, this boundless, ethereal brain in the cloud. Like it's just software, right?
Yeah, completely infinite. We
Yeah,
definitely picture it as this floating, weightless digital phenomenon.
exactly. You can write poetry, you can code, you can discover new pharmaceuticals. And because it's software, we kind of just imagine its potential is only limited by, our own imagination.
Right, but it's the ultimate reality check when you actually look at the physical constraints. I mean, the entire trillion-dollar AI revolution is currently being held hostage by a microscopic piece of hardware.
Which is wild. So, welcome to the deep dive. Today, we're going on a mission to uncover the invisible backbone of AI.
Yeah, because everyone talks about GPUs and compute power. We hear about NVIDIA chips and massive server farms all the time.
Oh, constantly. But none of that matters if the data can't actually move from one processor to another. So today, we're unpacking a massive stack of sources to understand the critical bottleneck threatening this whole industry.
And we got some heavy hitters in this stack.
We really do. We've got a highly technical research paper on EML manufacturing, deep market reports from China Galaxy Securities and Data Center Frontier, corporate press releases from June 2026, some highly debated Reddit threads, and a recent keynote from the RAISE Summit.
Our goal by the end of this deep dive is to show you exactly why the future of AI is constrained by a literal byproduct of zinc mining.
Zinc mining.
I know, right? And the highly specialized lasers built from it. It's just a fascinating story of how a single microcomponent dictates the pace of global innovation.
So let's start with the macro problem facing AI data centers right now. At that RAISE Summit we mentioned, the CEO of Lumentum laid out this framework that I think perfectly captures what's happening.
Yeah, he said data centers are scaling across, they're scaling out, they're scaling up, and they're scaling in.
Right. Basically, the physical footprint of compute is expanding in every conceivable dimension simultaneously.
And the sheer physics of that expansion creates a massive data traffic jam. I mean, an astronomical amount of information needs to move between servers, and it has to move instantaneously.
And historically, we've used copper wires to move that data, right? Like electricity flows through the copper carrying the signal.
Exactly. But copper has a very hard physical limit.
Yeah, I want to break down that physical limit because the industry actually calls it the copper wall. And when we talk about hitting a wall, it's not just a metaphor here.
No, not at all. As you push more bandwidth through a copper wire, and as you try to increase the speed of that data transfer inside the data center, the distance that signal can actually travel before it degrades, it just decreases dramatically.
The electrical signal literally breaks down.
Right. As you pump high-frequency signals through copper, you run into what's known as the skin effect. That's where the current gets pushed to the outer edge of the wire, which increases resistance.
And resistance means heat.
Massive amounts of heat. The signal degrades, it creates interference, and it just can't make the trip across the server room without melting the cables or, just losing the data entirely.
Okay, let's unpack this for a second. It's like trying to run Hyperloop pods on a dirt road. Copper is the dirt road, and the Hyperloop pods are the massive chunks of AI data.
I like that analogy. The friction is just too high.
So, to break through this wall, data centers are literally ripping out miles and miles of copper, connecting these server racks, and they're replacing them with optical links. They're using light to transmit the data instead of electricity.
And it solves the physics problem beautifully, actually. Light flowing through a glass fiber optic cable just doesn't suffer from that physical resistance.
Right.
It doesn't generate that server melting heat over those distances, and the bandwidth capacity is, well, it's orders of magnitude higher. It is the only physical way to meet the data demands of modern AI workloads.
But here is where I get hung up. If we've always known that light is faster and more efficient than electricity running through metal, why didn't we just build the Hyperloop tracks out of light from the start? Like, why are we only hitting this crisis now?
Well, generating and controlling light at the absurd speeds required by an AI cluster isn't as simple as flipping a light switch.
You can't just put a tiny light bulb in a server.
Exactly. You need incredibly sophisticated microscopic lasers that can pulse billions of times a second with absolute perfect clarity, and they have to survive in a hot server environment for years.
Enter the superhero of our story, the electroabsorption modulation laser, or EML.
The EML.
Yes, this is the core technology analyzed in that 100G PM4 research paper we have in our stack. Now, AI data centers are currently operating these massive 400G and 800G transceivers, and they are desperately reliant on these EML components.
And just to decode that terminology a bit for you, when you say 400G or 800G, the G stands for gigabits per second.
Right, that's the raw speed of the data pipeline.
Yep. And that PM4 mentioned in the research paper stands for pulse amplitude modulation. So instead of just sending a simple on and off signal, PM4 uses 4 different levels of light intensity to pack twice as much data into the exact same signal.
Okay, so the laser has to be incredibly precise. It's not just flashing on and off, it's flashing at very specific, varying brightness levels, billions of times a second.
Exactly.
And the scale of this is just hard to wrap your head around. Transceiver shipments are projected to hit 31.9 million units in 2025 alone. That is a massive 56.5% annual growth rate.
It's huge! And to understand why these specific EML chips are so crucial to hitting those 800G speeds, we need to look at how they actually function.
Okay.
An EML is not a single laser. It's actually 2 distinct components integrated into one microscopic device.
Oh, interesting.
Yeah. First, you have the laser diode. This part stays on constantly. It produces what they call a continuous wave. Just imagine a steady, unbroken beam of light.
Got it. And the second part?
The second part is the electroabsorption modulator. This sits right in front of the laser and acts like a hyperfast digital shutter. It chops that steady, continuous beam of light into the actual data signals.
The ones and zeros.
Right, or in the case of PM4, the 4 distinct amplitude levels.
Okay, here's where it gets really interesting. If I'm using a flashlight to send Morse code across a dark lake, I need the light to go completely dark between my flashes.
Right, exactly.
Because if the flashlight stays dimly lit when it's supposed to be off, the person on the other side of the lake gets totally confused. They can't tell what's a deliberate signal and what's just ambient glow. And that confusion, translated to data center terms, is the bit error rate, right?
Yes, exactly. And the metric that measures the contrast between your flash and your darkness is called the extinction ratio, or ER.
ER, okay.
It's the mathematical ratio of the optical power in the on-end state versus the optical power in the off state.
Yeah.
So a higher extinction ratio means a much clearer, sharper signal distinction.
Which lowers your bit error rate.
Exactly.
And the research paper gets very specific about this. They found that achieving an extinction ratio above 8 decibels at just a 1-volt swing allows for ultra-low error rates.
That's a huge deal.
Yeah, and that specific performance threshold is what allows these lasers to meet the strictest requirements for an 800G InfiniBand switch.
And InfiniBand is the gold standard networking protocol that AI supercomputers use to communicate internally. The components have to be flawless.
Right.
Furthermore, the paper highlights the insane reliability of these microscopic flashlights. Based on their stress testing, they estimate the lifespan of these EML chips to be over 1,700 years when operating at a standard 53 degrees Celsius.
Okay, let's pause on that. 1,700 years.
Yeah, it's wild.
We have the perfect microscopic flashlight. It can modulate light into 4 different amplitude levels, billions of times a second. The signal is crystal clear, and it basically lasts longer than the Roman Empire. So, I mean, we should be popping champagne. Why was Lumentum CEO sounding the alarm at the RAISE summit?
Well, the crisis stems entirely from what that microscopic flashlight is made of.
Ah.
The physical material required to build an EML that can perform at these specific wavelengths and speeds is incredibly difficult to source and even harder to manufacture.
I'm looking at this tweet from the RAISE summit, and it's stark. The CEO of Lumentum warned the audience that the supply gap for these specific lasers is facing a more severe crisis than the memory chip shortage we saw a few years ago.
Yeah, that memory chip shortage was painful.
And Lumentum has 5 massive fabrication plants dedicated to this. Yet their shipments are running more than 30% below what their customers are currently demanding.
The demand side is voracious right now because the big players see the bottleneck coming. NVIDIA has reportedly stepped in and locked up EML manufacturing capacity all the way beyond 2027.
Wow.
They are literally buying the future supply before it even exists. And that move has created a cascading effect, resulting in a 40 to 60% supply gap for the entire rest of the industry trying to build their own 800G modules.
I want to pull in the numbers from the China Galaxy Securities Report because they put this into brutal perspective. They projected that global demand for these specific devices would hit roughly 2 million wafers in 2025.
Right.
But the actual manufacturing capacity globally, only about 600,000 wafers. That is a supply gap exceeding 50%.
It is a massive structural shortfall that you just cannot solve overnight.
And I'm looking at this 50% supply gap, and my first instinct as an observer is, well, just build a new factory. throw some of NVIDIA's trillions at it, pour some concrete, and print more wafers. But I'm guessing from the Galaxy Securities Report that this isn't simply a capital expenditure problem, is it?
No, not at all. It's a geology problem.
Geology.
The bottleneck starts deep underground. It comes down to the fundamental atomic nature of the element required to make these wafers, indium.
This is where we trace the supply chain all the way down to the dirt. The material we are talking about is indium phosphide, or InP. According to the research, indium phosphide is the only, and let me make sure I get this right, direct bandgap 3V material capable of supporting long-reach, single-mode transmission at the required 1310 and 1550 nanometer wavelength.
Yep, that's the exact technical description.
Okay, we need to translate that. What does direct bandgap actually mean in this context?
So, think about silicon, right? The material that powers almost all our traditional computer chips. Silicon has an indirect band gap. If you pump electrical energy into silicon, it wants to release that energy as heat.
Right.
Indium phosphide is different. It has a direct band gap. When you pump electrical energy into indium phosphide, it releases photons. It actually emits light.
So you literally cannot use standard silicon to build the laser itself because it will just get hot instead of glowing.
Precisely. You need indium phosphide to actually generate the laser beam. And those specific 1310 and 1515 nanometer wavelengths mentioned in the paper are crucial because those are the optical sweet spots.
The sweet spots for what?
For fiber optics. At those exact wavelengths, light can travel through modern glass fiber optic cables with almost zero signal loss. And indium phosphide naturally emits light at those perfect frequencies.
Okay, so we absolutely need this specific element, indium. But here's the staggering fact we uncovered. About 90% of the world's primary indium is actually a byproduct of zinc mining.
Yeah, that's the kicker.
You don't just go out and open an indium mine. You mine for zinc, which is mostly used to galvanize steel, and indium is this rare hitchhiker you occasionally pull up with it.
And the implications of that are huge. The supply of indium is inherently inelastic. Even if the AI industry is screaming for more lasers, you can't just ramp up indium production.
You'd have to mine way more zinc.
Exactly. Its availability is dictated almost entirely by the global construction and automotive industry's demand for zinc.
And looking at the Galaxy Securities Report, there's a fascinating geopolitical reality here, too. If we just look at the objective market data, and to be clear to you listening, we're just reporting the data here, not taking any political sides, but objectively, China accounts for about 70% of the global refined output of this material.
Which is a massive market share.
And when the Chinese Ministry of Commerce implemented export controls in early 2025, the indium prices in Eastern and Western markets completely decoupled. The global supply chain essentially fractured.
The market data clearly shows that fragmentation. But, getting your hands on the raw indium is really only step one. You can't just take raw indium from a zinc mine and stick it in an AI server.
Obviously.
It requires a punishing purification process.
We're talking multiple stages of extreme chemistry. Electrolysis, vacuum distillation, zone refining.
Yeah, it's intense.
All of this is required just to reach what the industry calls 6N grade purity. And 6N means the material is 99.9999% pure.
6 nines?
Yeah. Because a single rogue atom can ruin the optical properties.
And when you step back and look at that whole chain, it is profound. We have the most advanced ethereal technology in human history, these massive large language models and neural networks, and its immediate growth is tethered to the global output of zinc mining and a multi-stage chemical purification process.
The future of cloud computing is still fundamentally bound by hard earth geology.
Exactly.
But let's say a company manages to navigate all that. They get the zinc, they extract the indium hitchhiker, they purify it to 99.99999%. They are still not done.
Not even close.
Turning that ultra-pure dirt into a usable crystalline substrate wafer is a monumental task. I want to dive into the ultra-exclusive club of companies that can actually pull this off.
Growing indium phosphide crystals from those raw materials is what the semiconductor industry calls a 0-to-1 process. You are literally forcing atoms to align into a perfect, flawless geometric lattice.
Wow.
It requires immense, precise heat and pressure.
I read it's like trying to freeze water into ice. But you need every single water molecule to line up perfectly without a single microscopic fault line, and you have to do it at 1,000 degrees Celsius.
That's a great way to visualize it.
Because of how punishing that physics problem is, the market is an oligopoly. 3 companies basically control the entire planet's supply.
Just 3.
Yeah. You have Sumitomo Electric at 42% market share, AXT, which is also known as Beijing Tongmei, at 36%, and JX Nippon Mining and Metals at 13%. Between them, they control over 90% of the global substrate market.
And the reason we are facing such a bottleneck right now is that these three companies are in the middle of a massive, risky manufacturing transition.
The wafer size transition.
Right. For years, the industry standard was growing these crystals just large enough to slice into 3-inch or 4-inch wafers. But to meet the sheer volume of chips the AI industry is demanding, they have to transition to 6-inch or 150-millimeter wafers.
This 6-inch arms race is fascinating. We pulled some sources from a highly technical Reddit debate from March 2026, where engineers were dissecting the math on this transition. Moving from a 4-inch to a 6-inch wafer provides roughly 2.25 times the surface area.
Sure, just basic geometry.
But because of how the rectangular chips are cut from a circular wafer, you actually lose fewer chips to the curved edges on a larger circle. It yields 4.6 times more chips per wafer.
It's an exponential leap in manufacturing output.
Yeah.
But the execution risk is terrifying. When you try to grow a larger indium phosphide crystal, the thermal dynamics change and the risk of atomic defects goes up exponentially.
And a defect means?
A defect in a crystal lattice means the optical chips cut from that area simply won't emit light properly. They're useless. So it's a massive financial gamble.
And the Reddit sleuths were tracking this execution risk really closely. They pointed out that Lumentum has successfully navigated this tightrope. They quadrupled their output in just 18 months and hit a massive 42.5% gross margin.
Which is incredible in this space.
Yeah. Coherent is also doubling down. They're building out advanced fabs in Texas and Sweden. These two companies were currently leading the pack in operational maturity, specifically for building continuous wave lasers and the external laser sources that NVIDIA is basically starving for.
And that debate also highlighted the alternative approach. Nokia, through their Infinera acquisition, is ramping up a new fabrication plant in San Jose. But they're focusing on something called monolithic photonic integrated circuits, or PICs.
Yeah, the engineers on Reddit noted that while PICs are highly advanced because they integrate the laser, the modulator, and all the routing onto one single chip, they carry a much higher yield execution risk.
The logic there is simple, but it's brutal.
How so?
If you make a discrete standalone laser and it fails, you throw away a tiny laser. If you integrate everything onto one massive monolithic chip and one tiny microscopic laser component fails, the entire expensive integrated chip is garbage.
Oh, wow. So the yield curve is much steeper to climb in the short term.
Exactly.
So with everyone fighting tooth and nail for these indium phosphide wafers, and the supply being so constrained by zinc mining, extreme purification, and this insane crystal growth process, it makes me wonder, won't the tech industry just try to pivot?
Pivot away from indium.
Yeah. If indium is this massive headache, can't we just engineer our way out of this and switch entirely to a cheaper, more abundant material? Like, I don't know, silicon?
That is the logical assumption, and it actually brings us to a massive buzzword in the industry right now, silicon photonics. But here's the twist that most people miss. Silicon photonics isn't replacing indium phosphide.
Wait, they don't compete with each other?
No, it actually desperately needs it to function. They are completely complementary.
Oh, really?
Yeah. The industry calls this heterogeneous integration. As we established earlier, silicon has an indirect band gap. It cannot emit light efficiently.
Right, it just gets hot.
Exactly. However, silicon is fantastic at routing optical signals. You can etch microscopic mirrors and waveguides into silicon to direct the light beautifully. So silicon acts as the highway system, but it can't be the headlights. Indium phosphide handles the actual light emission. You need both materials working together in the exact same package.
Okay, the indium phosphide generates the laser pulse, and the silicon photonics chip routes that pulse to where it needs to go in the circuit.
Would that it?
And we actually see this exact synergy in a press release we have from June 2026. Sivers Semiconductors and Global Foundries announced a major partnership. They're taking Sivers laser arrays, the indium phosphide light emitters, and integrating them directly into Global Foundries' Scale platform.
Which handles all the silicon routing.
Exactly.
And this partnership really highlights how data center architecture is fundamentally evolving. Currently, we mostly use pluggable transceivers.
Pluggables.
Yeah, you plug an optical module into the front of a network switch. It's kind of like plugging in a giant USB drive.
Okay, that makes sense.
But as data speeds increase, pushing the signal from the GPU all the way across the circuit board and out to the pluggable module on the front panel, it introduces way too much latency and power loss.
So they have to move the lasers closer to the processor itself.
Exactly. The industry is shifting toward near-packaged optics and eventually co-packaged optics, or
Yeah.
CPO.
Co-packaged optics.
Mhm.
That's where the optical chip and the GPU are literally sitting on the exact same substrate, right? Like side by side, sharing the same physical package.
Yes. You eliminate the physical distance between the computation and the optics. And here is the crucial takeaway.
Okay.
Whether the industry adopts silicon photonics utilizing continuous wave lasers or uses VCSELs, which are vertical cavity surface emitting lasers typically used for shorter distances, or even pivots to future technologies like micro-LEDs, the fundamental architecture is changing. The number of lasers deployed per GPU is going to skyrocket. We are moving from a few lasers per server rack to potentially dozens of lasers packaged with every single chip.
Which means this insatiable demand for indium phosphide is permanently locked in. Like, this isn't a temporary spike caused by a supply chain hiccup.
No, no.
It is a fundamental structural reshaping of the semiconductor value chain. It's creating massive opportunities across the board, not just for the companies growing the crystals, but for the foundries, the advanced packaging facilities, and the companies building the hyper-specialized optical testing equipment.
The physical pressure on the indium phosphide supply chain is the new normal. It is the inescapable physical reality of scaling artificial intelligence.
Let's bring this all together.
Yeah.
We started this deep dive looking at the macro explosion of AI, the massive data centers being built, and the forced transition from copper wires to optical light.
Right.
And we track that light to a microscopic electroabsorption modulation laser blinking billions of times a second.
A highly complex laser that is absolutely dependent on a perfect 6-inch crystalline wafer of indium phosphide.
Which in turn is dependent on the global mining of zinc.
It's incredible how deep the rabbit hole goes, and it leaves us with something really profound to think about.
Yeah, we opened by talking about how we view artificial intelligence as this boundless, infinite software. We picture it as a brain in the cloud, constrained only by the cleverness of our algorithms and the limits of human imagination.
But when you look at the supply chain data, it raises an entirely different question. What if the ultimate speed limit to reaching artificial general intelligence isn't a software problem at all?
Right.
What if the true ceiling of human AI advancement isn't dictated by code, but is dictated entirely by the physical, geological limits of mining zinc and crystallizing indium phosphide?
What if the key to unlocking the infinite mind of AI is actually buried in the dirt? It's a wild thought to leave you with, and something to mull over the next time you ask an AI to write an email or generate an image. Thanks for joining us on this deep dive. We'll see you next time.